So one of the things that we looked at in part one of describing locations was percentiles, and that is taking taking a data value and sort of ranking it in terms of what percentage of numbers that data value falls above. We also did some different things in terms of measures of location with z-scores, and a z-score measures how many standard deviations either above or below the mean a given data value is. And one of the things that we're going to look at next is some different things with what's known as transforming data. And what transforming data is if you take all of the data values in your set and you do something mathematically to them, and that could be adding, subtracting, multiplying, dividing, and by doing that, what does that do to the following things? What does that do to the shape of the distribution? What does that do to the center of your distribution? What does that do to the spread of the distribution? So some of the different things as far as effects go involving adding or subtracting a value to each of the data values in your set. And this is adding positives or negatives values. So the first thing would be is if we added or subtracted a constant to all of the data values in the set, what's going to happen is your measures of center and location will change by whatever you added or subtracted by. So keep in mind, measures of center would be mean, median. Measures of location would be quartiles, percentiles. So all of those values would change based upon whatever it is that you added or subtracted to all of the data values. In terms of some other things here that do not change, the shape of a distribution will not change when you add or subtract a constant to all of the data values in your set, and the measure of spread will not change either. So keep in mind that with shape never changes regardless of whatever it is you do, whether you're adding or subtracting in this particular instance, and you'll see next when we start to talk about multiplying and dividing. Shape never changes regardless, but when you're adding and subtracting, the spread does not change either. So keep in mind what we're talking about when we're talking about measuring spread. We're talking about the range, we're talking about the interquartile range, and we're talking about the standard deviation. So those values will not change when you add or subtract a constant to all the data values. But what about the effects of multiplying or dividing by a constant? So this would be if we took all of the data values in the set and we multiplied or divided them by a constant. So in terms of center and location, okay, those values are going to change by whatever you multiply or divide by. So measures of center, measures of location change no matter what you mathematically do to all your data values. If you add, subtract, multiply, or divide, your center and location are always going to change by whatever it is that you added, subtracted, multiplied, or divided by. The measure of spread in this case will also change if you multiply or divide all of your data values by a constant. And it will change by a factor of the absolute value of b. But, as we mentioned previously, the shape will not change. Shape never changes regardless of what you do to your data values. So in this particular instance with multiplying and dividing, measures of center and location are going to change by whatever you multiply by, and the measure of spread will change by the absolute value of whatever you multiplied by. So here's an example of some different things with transforming data. So the question says, in 2010, taxi cabs in New York City charged an initial fee of $2.50. So that's just the cost of just getting in the cab before it even goes anywhere, plus $2 per mile. In equation form, the fare that you would pay when you get into one of these taxis would be $2.50 plus 2 times however many miles you went. And the question says, at the end of the month, a businessman collects all his taxi cab receipts and calculates some numerical summaries. The mean fare that he paid was $15.45 with a standard deviation of $10.20. So keep in mind that his average was $15.45, but he didn't pay $15.45 each time. Sometimes he paid more than $15.45, sometimes he paid less than $15.45. So this $10.20 kind of measures his variability. So the question says, what are the mean and standard deviation of the lengths of his cab rides in miles? So what was his average distance that he took in each of his cab rides, and what was the variability, what was the standard deviation in miles of those same cab rides. So keep in mind that when we're talking about this equation here, 250 plus 2 times the number of miles that he drove, keep in mind what gets affected when we're talking about transforming data. So remember, the mean will get affected, and I'm just looking at this equation here, this fare equals 250 plus 2 times the number of miles. So because the mean will be affected by both adding 250 and multiplying by 2, both of those factors are going to come into play when we calculate what the mean length of his cab rides is. But remember that standard deviation, the spread, is only affected by multiplying. So that's just going to be this part here that's going to be affected when we go to calculate the variability in the number of miles that he went here. So let me kind of talk about the answers here. So if we're solving the equation, and here's the original equation, the fare equals $2.50 plus 2 times the number of miles. Basically what we get here is the number of miles is going to equal the fare minus 250 times 2. And all I did here was I just took this equation, this one here, and I just solved it for the miles. So I basically did a minus 250 on both sides, and then I divided by 2 at the end. So to find the mean number of miles, I'm just going to substitute this $15.45. I'm going to substitute that in for the fare here. And when I do that, I end up getting a value of 6.475 miles. So that basically talks about part A of this, the mean of the number of miles he rode in the cab. What about the standard deviation? So to find the standard deviation, all I want to basically do here is I want to divide the standard deviation of the fares by 2. When I do that, I get $5.10 miles. I don't subtract the $2.50 because subtracting a constant doesn't change the spread. So the only part of this equation, this fare equals, try that again. This fare equals, just substitute this with F. The fare equals 250 plus 2 times the number of miles. When I'm converting from dollars to miles in this case, because you only have the spread that's affected by multiplying, this is the only part of that conversion that I'm working with as far as the equation go. This right here, this plus 250, it does not factor into transforming the data when we're talking about spread, because spread doesn't change when you add and subtract. So take a moment and take a look at this checkpoint question here. And the question says, the figure below shows a dot plot of the height distribution for Mrs. Navarre's class along with summary statistics. So it gives you the dot plot here, and then it gives you these values here at the bottom. So just remember, N is the number of data values, X bar is the mean, SX is the standard deviation, sample standard deviation, and then here you have the 5-number summary. So why don't you take a moment and see what you can do with these following checkpoint questions on your own. So to take a look at number 1, the question says, suppose that you convert the class heights from inches to centimeters, and here's the conversion for that. 1 inch equals 2.54 centimeters. Describe the effects this will have on the shape, center, and spread of the distribution. So to convert from inches to centimeters, you're essentially going to take each of the heights and you're going to multiply them by 2.54. So in this case, we're multiplying all the data values in the distribution by 2.54. So when I do that, remember, multiplying everything will change except for the shape. So shape's going to stay the same because the shape always stays the same. The center and spread in this particular instance will be multiplied by 2.54. And then the question number 2 says, if Mrs. Navard had the entire class stand on a 6-inch high platform and then had the students measure the distance from the top of their heads to the ground, how would the shape, center, and spread of this distribution compare with the original height distribution? So keep in mind that if she has them all stand on a 6-inch high platform, what that's going to do to their heights is going to make each of them, in terms of their height from the top of their heads to the ground, it's going to make them all 6 inches taller. So what I'm basically doing here is I'm adding 6 inches to each one of their heights. And when I do that, remember what happens when you add. So the shape and the spread will not change because that doesn't change when you add, but the center will have 6 inches added to it. Question number 3, it says, now suppose that you convert the class heights to z-scores. What would be the shape, center, and spread of this distribution? So keep this in mind with z-scores. You might want to make a special note of this somewhere because this is very important. It's going to come up in a lot of different things we're going to do moving forward. So anytime you have a distribution and you take all of the data values and you convert them to z-scores, what will always be true of those values is this: the mean will always be 0 and the standard deviation will always be 1. And that's true anytime you take a group of data values and you convert them to z-scores. So if you take your z-scores and you find the mean will always be 0. And if you take your z-scores and compute the standard deviation will always be 1. So some other things that kind of go with what we've been talking about with shape and centers and spreads and things like that has to do with what's known as a density curve. So when we're talking about quantitative data and some of the things that we want to analyze when we're looking at quantitative data, first thing is this, okay, and that is always plot your data. And remember, we talked about the significance of plotting data, and that's because you always want to know first what the shape of your distribution is, because the shape of your distribution will determine what your measure of center is going to be, whether you're going to use the mean for symmetric graphs or you're going to use the median for graphs that have skewness or outliers. And then the shape also determines what type of spread you're going to use, whether you're going to use the interquartile range or whether you're going to use the standard deviation. So when we're talking about quantitative data, first plot your data, then you want to look for the overall pattern of the data and any type of striking departures from the pattern, which are known as outliers. Then once you have an idea of what the graph, what the overall pattern is, what the shape of it is, you can then start to calculate your numerical summary to describe the center and the spread. So what we're going to kind of add to this is a number 4 here, and that is sometimes the overall pattern of a large number of observations is so regular that we can describe it by a smooth curve. So if you've ever heard of a bell curve before, and that's a lot of what's going to come up with what we're going to do next in terms of density curves. But a bell curve is not the only type of density curve. There's all kinds of different types. So just some characteristics of a density curve. 2 very big ones here. So a density curve has the following characteristics. One is it's always on or above the horizontal axis. It'll never go through the horizontal axis, and its area underneath the curve is always equal to exactly 1. So in terms of what a density curve looks like, I gave you an example here, and this is the overall pattern in a histogram form. This is 947 7th graders that took a vocabulary part of a basic skills test. So if you notice here this histogram, and what I drew around this histogram or over this histogram is a smooth curve that looks like this. And this is what's known as a density curve. So just notice the characteristics of this. The whole curve is on or above the horizontal axis, and the area underneath the curve is equal to 1. So here's an example of a density curve, and I want you guys sort of pause this now and take a few moments to answer some questions about this particular curve. So if you notice here, the total area under the curve is 1. And what we did was we sort of sectioned off a portion of this curve, and the area of the curve between these values, 7 and 8, is approximately 0.12. So the questions ask you, explain why this is a legitimate density curve, and about what proportion of observations lie between 7 and 8. So take a moment and see what you can answer with these checkpoint questions on your own. So to answer question 1, explain why this is a legitimate density curve. So what you want to speak to here are two things. One is that the curve is on or above the horizontal axis, and it has a total area of 1, which was stated in the curve. And then the second question says about what proportion of observations lie between 7 and 8. So it gives you on the graph that the area between 7 and 8 is approximately 0.12. So we would say about 12% of the observations lie between 7 and 8 on this particular density curve. So the other question here, it says mark the appropriate location of the median and the mean. So hopefully you noticed with this graph that the graph is slightly skewed left. So remember, in terms of the mean and the median, its relationship when you have a graph that's skewed left. The mean will always get pulled towards the tail end of the graph. So in this particular curve, the mean is going to be slightly less than what the median is. So this is approximately where the mean and the median should be. So as long as you have the median or the mean being slightly less than the median, that's a kind of a good place to start with something like this here. So in terms of exactly where do you put the mean, exactly where do you put the median, we're going to sort of take a look at that here in a moment. But the other question that kind of went with this, it says explain why the mean and median have the relationship that they do in this case. Well, that's all driven by shape. Okay, because this graph is skewed left, the mean will get pulled to the tail, which in this case makes the mean less than the value of the median. So one of the things that we'll look at kind of moving forward is some different things involving where does the mean go in a density curve, where does the median go in a density curve in relation to the shape of the shapes of the graphs.